Swayam Prabha. Digital India. Educated India.
And lastly, learner will be able to understand reactions of cycloalkanes. So these are some learning outcome from for stability of cyclohexane and higher members, Sachet and Morse in 1918 proposed that such rings can be free from strain if all the ring carbons are not forced into one plane, as was assumed by Baer. So in case of Baer's theory, it has been assumed that all the carbons they are in one plane, but Sachet and Morse theory has proposed that when it comes to an higher cycloalkanes, like here we have taken example of an cyclohexanes, so they can be free from strain. So free from strain, it means that whatever the tetrahedral angle we always find in case of an carbon-carbon bond, that is 109 degree. So that 109 degree, it has been written, or it is as it is. It has been proposed by Sachet and Morse theory, but the carbons they are not in one plane. So carbon have they are not in one plane as it was been assumed by Baer, and Baer also shown that when it comes to an ring like an cyclohexane, it is having a negative strain. So negative strain means it is almost having a degree 120 degree angle, and in actual it should be 109, but it is 120 as per Baer's assumption. But Sachet and Morse theory has explained that it can be free from the strain, and how it is we will see it. If the ring assumed a folded or puckered condition, the normal tetrahedral angle of 109 degree and 28 minutes are retained, and as a result the strain within the ring is relieved. So instead of what Baer has been assumed that when it comes to and propane, butane, cyclobutane, cyclopropane, and cyclopentane, or also cyclohexane. So he told that all the carbons they are in one plane. But as per the Sachet and Morse theory, they told that a ring should be folded, or it should be in puckered condition. So puckered and folded, it means same. So how that ring it should be, now we'll see it. And when ring it is in that form, when it is not in one plane, then it has been relieved from the strain as assumed by this theory. Like we have taken here example of an cyclohexane. So cyclohexane can exist in two non-planar puckered conformations, both of which are completely free from strain. So puckered and folded, these are the same meaning, and non-planar means all the carbons they are not in one plane, they have a different plane. And conformation means so here there are two types of an conformation. So conformation, it means that it is rotation of an single bonds around the carbon. So in case of an like cis geometric isomers, the conformation it does not show because it is having a double bond, and due to which there is restricted rotation of an carbon-carbon double bond. But conformation is shown by some stereoisomers which can rotate around itself. So this main assumption from this theory that all the carbons they are not in one plane, as Baer assumed that it is in one plane, but this theory states that it is non-planar, so they are not in one plane, and that is why it can retain the angle. So whatever the angle, it is 109 degree and 28 minutes for tetrahedral geometry, so it has been retained by cyclohexane, and so there is no negative strain as it was been assumed by Baer. And it has been proved that conformation of an cyclohexane, that there are two forms actually, the boat and chair conformation. So we will look at, so these are called chair form and boat form because of their shapes, because their shape look like chair, and one conformation it look like boat, so they are said to be that. So this is a chair conformation, and this one is a boat conformation. See here the angle for all the carbon, it is 109 degree and 28 minutes, so no doubt about it, but the stability it is different. It is more stable, chair conformation is more stable than the boat conformation. So In between both, it is also having some twist type of an boat. So boat, it is one of the less stable conformation. And why so it is due to the hydrogen hindrances of carbon number 1 and carbon number 4 in case of an boat conformation. So that is a different part when you will come across conformation of an cyclohexane. So you will learn this things, why the chair conformation is more stable than the boat conformation. The point over here is that it is just that, so they all the carbons, they are not in one plane. So here also you can see this broad line, they are indicating that these carbons, they are behind, these carbons are having the hydrogen from behind, right? And the normal line, it is showing that it is on the paper. And also in case of this boat conformation also, so all these carbon, they are behind. So all the boat conformations and chair conformations, they have axial and equatorial angle. So these are interconvertible. Chair conformation can be converted to boat, and boat conformation can be converted to chair. But most of the time, you will see that chair conformation is more prominent, because chair conformation, it is more stable. And that is why at the room temperature you can see the molecules, they most of them, they are in the chair conformation rather than in a boat. So boat, it only increases the potential energy from more than the chair conformation. Such non-planar strain-free rings in which the ring carbon can have the normal tetrahedral angle are also possible for higher cycloalkanes. So just we have studied over here only cyclohexane. We have taken the example of an cyclohexane. So same can be a thing in case of an cycloalkanes which are higher than cyclohexane, or higher cycloalkanes like cyclohexane, cycloheptane, and cyclooctane. So these are some compounds which are free from strain. And why they are free? Because all the carbons, they are not in one plane, as it was been assumed by Bayes. So the Bayes assumption we seen in the last session, that Bayes assume that as the number of carbon increases, the stability of ring decreases. When it comes from an cyclohexane, it becomes a negative strain. It will be more prevalent in case of an higher cycloalkanes. But this theory explains that they are free from strain and it retains the normal angle. And why it is so? That it can exist in different conformations like chair and boat. So whatever we have taken example of an cyclohexane over here. And most important, that it should be a non-planar. Chair form of cyclohexane is more stable than the boat form. And whatever I told you, that it is due to some steric hindrances of carbon number 1 and carbon number 4 hydrogens, and that is why chair form, it is more stable than the boat form. And under the ordinary condition, cyclohexane molecule will mostly exist in the chair form. So whatever I told you, examination of the chair form of cyclohexane reveals that the hydrogen atoms can be divided into two categories. So it is due to an arrangement of an hydrogen atoms, the potential energy in case of an boat form increases, and it is due to an arrangement of an hydrogen atoms and movement of an carbon. Actually, it is there are two types of an hydrogens. So these two types, it means one is axial and second one is an perpendicular. So there are total 12 hydrogens in case of an cyclohexanes. So half of them, they are said to be an axial hydrogens, and half of them, they are said to be an equatorial hydrogens. So 6 bonds to the hydrogen atoms point straight up or down, almost perpendicular to the plane of molecule. These are called axial hydrogens. The other 6 hydrogen lie slightly above or slightly below the plane of cyclohexane ring and are called equatorial hydrogens. So this is an conformation, chair conformation, and this black color hydrogens, they are said to be an axial. So whatever it has been told over here, that they are either straight up or straight down. So here you can see straight up or straight down. So these are called axial hydrogens. And this red color, they are slightly below or slightly above the plane. So some, like this one is below the plane and this one is above the plane. So these are called equatorial hydrogens. uh, Red color hydrogens, they are equatorial hydrogens and they are 6 in number, and remaining 6, they are axial hydrogens. Now coming towards boat conformation, similar is the thing, that it will have 6 hydrogens equatorial and 6 hydrogen axial. So this red color, they are nothing but an equatorial, and these hydrogens with black color, they are axial hydrogens. So from this theory, it can be understood that higher compounds like cyclohexanes and many more cycloalkanes, higher from and cyclohexanes, like cyclooctane, cycloheptane, non-endecane. So these are some compounds. They does not have any strain as per this theory. And why it is so? Because all the carbons, they are not in one plane, and they show different conformations, and these conformations can be they cannot be in a ring form. They are in the folded form, or they are in the pocket form, and that is why it is relieved from strain, and that is why they show an higher stability. So cyclohexane, it is quite stable compound, and most of the time you can see in the at the room temperature it is in the chair form rather than in the boat form, because boat form has a higher potential energy. So now we'll come to our point, that is method of preparation of cycloalkanes. A terminal dihalide, when treated with sodium or zinc, forms cycloalkanes. This reaction is an extension of Wurtz synthesis or Wurtz reaction, and useful for preparation of 3 to 6 membered rings. So these are dihalide compounds, that is 1,3-dichloropropane, and when it is been reacted with sodium, and when it is been heated with the sodium, it forms an cyclopropane. So this reaction can be used for 3 to 6 membered rings. So from propane to hexane, it can be utilized. Just extend the structure of an dihalides and you will get the compound. If it is propane dihalide, so you will get the compound butane. Sorry, when it is butane, we will get the compound butane. Next preparation of cycloalkanes, it is from calcium salts of dicarboxylic acid. When the calcium or barium salts of dicarboxylic acids are heated, cyclic ketones are formed. The cyclic ketones can be readily converted into corresponding cycloalkanes by Clemmensen reduction. So this is the structure of an calcium adipate, and it is calcium salt of dicarboxylic acid. So here you can see the structure. It is dicarboxylic acid and having the calcium salt in between. When it is heated, it forms cyclopentanol, cyclopentone, and after that by Clemmensen reduction. So it is done by zinc amalgam in presence of an HCl. and after that it forms cyclopentane. it forms an homoatom, and basically it forms an free radical. And also we can get substitution product of an halogen on cyclohexane. So by reacting chlorine with cyclohexane in presence of UV light, we again get chlorocyclohexane. So these are substitution type of a reaction. So now next we will see that is addition type of an reaction with an halogen. When it comes to an addition, it will have a different product. Cyclopropane react with chlorine or bromine in the dark to form addition product, and CCl4 carbon tetrachloride is used as a solvent. So cyclopropane react with the bromine, and this reaction condition should be in the dark. So there should be no any kind of an oxidation that may cause, and it has been carried out in a non-polar solvent like CCl4, and it forms an 1,3-dibromopropane. So reverse reaction also we have seen in case of this cycloalkane in preparation method. From dihalides we can prepare this cycloalkanes. After that, reactions of cycloalkanes addition to HBr and HI. Cyclopropane react with concentrated HBr and HI to yield 1 bromopropane and 1 iodopropane respectively. Cyclobutane and higher members do not give this reaction. So same are the again reaction condition that it has been carried out in the dark, and solvent it is carbon tetrachloride. But cyclobutane and higher member does not give this reaction. So it is one of the disadvantage of this HBr and HI. So it will not give for an. So means only it can give the reaction with an cyclopropane. So that is only one compound from an cycloalkanes. So it can react with this kind of an reagents. After that, reactions of cycloalkanes, it is with addition of an hydrogen. Cyclopropane and cyclobutane react with hydrogen in presence of nickel catalyst to give propane and N-butane respectively. Notice that higher temperature is required for cyclobutane, as we have seen in case of an Bayes assumption or Bayes theory that propane is more stable than butane, cyclobutane. So cyclopropane is more unstable and it is more reactive, and the reason also we have seen that it was due to an angle strain. So in case of an cyclopropane, so angle strain, it was the reason. Now we'll see the summary of this session. So we have seen the theory that is Sache and Morse, which was proposed in 1918, and it told that, or it the assumptions were made by Sache and Morse that higher cycloalkanes like cyclohexanes, they are free from strain when they are not forced in one plane. All the carbons, they are not in one plane, so the carbons in this rings, they are non-planar, and that is why they are free from strain. So free from strain, it means they are having normal tetrahedral angle, that is 109 degree and 28 minutes. And the forms, the rings, they are not actually in the round in shape, so they are either folded or they are either puckered. So these are the conditions for by which higher cycloalkanes, they show normal tetrahedral angle 109 and 28 minutes. So there are two forms or two conformations of an cyclohexane which are non-planar. So these two forms, they are nothing but one is chair form and second one is boat form. So according to their shape, the name has been given, that is chair form and boat form. So from out of that chair form, it has minimum potential energy, and boat form, it has a maximum potential energy, and it is due to the interaction of this hydrogen atoms on the carbon. So from this theory, it has been understood that higher cycloalkanes, they are not in the cyclic form, so they are in the folded form, and that is why they are strainless, or they are free from strain, and they are quite stable compound. After that, we have seen method of preparation of cycloalkanes. So first method, that is from dihalide. So 1,3-dichloropropane react with sodium, and when it is heated, it forms an cyclopropane. So second method, we have seen of an dicarboxylic calcium, and by reduction with zinc amalgam, it forms an cyclopentane, and in between it also forms cyclopentone, so which has been reduced to cyclopentane. After that, third method we have seen, that is also called Dickmann condensation. It uses diethyl adipate, and in between it is having some more products, that is it forms beta ketoester and beta keto acid, and after that it forms an cyclopentone, and it is been reduced again with the same step, that is zinc and amalgam, and it forms an cyclopentane. Fourth method we have seen, that is from alkene and methylene iodide with zinc and copper couple in presence of ether. So this reaction is also called Smith and Simon's reaction. It forms an